So is an example of an incomplete metric space. ठीक है? And there are many other examples of incomplete metric spaces are there. But our context of discussion is to get a complete metric space out of an incomplete metric. That means you need to suppose you have a metric space which is not complete. So you need to extend that space in which this the space that we are concerned, the given space is dense in that extended space, and the extended space will form a complete metric space. So that is our construction, that we need to construct one space which is complete and in which the given space, the given incomplete metric space will become dense in that complete metric space as an embedding, right? So yeah, okay. So for that reason, we first consider, because whenever we are constructing some spaces, so whether this space is unique or not, so that is one of the vital question. Okay, and to say that yes, this space is unique up to some map. Which map? The maps which preserve the distances. Okay, so that space will be unique up to these maps. So these maps are called isometries. Okay, whenever you are talking about metric spaces, you need to consider isometries. That means a map from one metric space to another, such that the distance between any 2 points from the domain space will be equal to the distance between the image points of that corresponding points. Okay, that means suppose so this is the distance between x1 and x2, and suppose this is fx1, fx2. So these two distances will be equal. Okay, this is your x, and suppose this is your y. So in between these two spaces, suppose f is a map, so then f is called an isometry. Okay, so formally speaking, the definition will be like that, that suppose we have two metric spaces x, x, d, y, rho. Okay, and a map f colon x to y is said to be an isometry if for every x1 x2 belongs to x, rho of fx1 fx2 will coincide with the distance between x1 and x2. And if this happens, then you say that f is an isometry in between these two metric spaces. Okay, and okay, okay, yeah, okay. Now if you look at this map closely, then you will see that, note that if if f colon x to y be an isometry, then f is eventually 1 1. Okay, as because why it is 1 1? Because if fx1 equal to fx2 for 2 points x1 and x2, then what is the distance between fx1 and fx2? The distance is 0, right? But since f is an isometry, so this distance is equal to d of x1 x2. So this is equal to 0, and hence x1 is going to be x2. So therefore an isometry is eventually an A1 1 map. Okay. 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 So now, so now we are going to state the theorem for completion of metric spaces. Right? And certainly incomplete metric spaces, because if a metric space is complete, suppose if a metric space is complete, then we are done. So we do not need to go further, right? But if it is not 1 1, then our job is to construct such some complete metric space in which the given space will be uh, dense in that new space, new complete metric space. Okay, as an embedding. Embedding means, so you are having some map, some isometry in between x, the given space x, and some subspace of that new space, suppose x cap. Okay, so let us write down the theorem that let x d be a given metric space. Okay, then there exists a complete metric space x cap colon d cap, which has a subspace w that is isometric. Isometric means you are having some isometry in between these two spaces, isometric in x, and is dense in x cap. Now this x cap is unique except for isometries. That is, if x tilde, if x tilde be another complete metric space, if x tilde be another complete metric space having a dense subspace w tilde that is isometric with x, then you can say that the former space, that is X cap, and the other complete metric space X tilde, so they are isometric, right? And whenever a metric space is concerned, two metric spaces can be think of same if they are isometric, right? So what is the proof? The proof can be divided into certain number of steps. Okay. Firstly, the proof splits into 4 steps. Okay. The first one is to construct a complete metric space. Okay. Secondly, you need to define an isometry T of X onto W, where W bar will be X cap, that is W is dense in X cap. Number 3 will be to prove the completeness of the newly constructed space X cap. And the last one is to show the uniqueness, right? Uniqueness of X cap except for isometries. Okay. So let us start with the step 1, that is construction of X cap. Okay. Yeah. And this construction is due to a great mathematician Cantor, who firstly cited this type of construction in between Q and R. That is, you need to make a completion of rationals, and you are getting the space of reals. And his construction was based on the concept of Cauchiness. Okay. And there is another way of construction of completion of a metric space, or actually completion of rational into reals, that was due to Dedekind construction. Okay. Okay. So let us have a look at this construction. So firstly, what we do, we just collect the Cauchy sequences in the given metric space X, right? So collect all the Cauchy sequences in the given metric space X. Okay. Okay. Now, and now what we are going to move. So our next move will be to define a relation in between two Cauchy sequences. Okay. So now we define that the sequence xn is said to be equivalent to the sequence xn dashed, denoted by xn is equivalent to xn dashed if and only if limit of d of xn dashed is going to be 0. Okay. If you see that this limit is tending to 0, then you define that yes, these two Cauchy sequences are equivalent. Okay. Now, if you look at this relation, you will see that firstly let xn be a Cauchy sequence in X. Okay. Then then d of xn comma xm tends to 0 as n comma m tends to infinity, right? Okay. Sorry. 1 minute. Yeah. Then d of xn comma xn equal to 0 implies limit of dxn comma xn equal to 0. Since the points are equal, so the distance is 0. And because of this, you can write that xn is equivalent to itself. That is, the relation is reflexive. Okay. Nextly, let xn is equivalent to xn dashed. Then limit of d xn dashed equal to 0. But since this function preserves, this is symmetric, right? So limit of d xn dashed xn equal to 0. That means xn dashed is equivalent to xn. So symmetric, right? Okay. Number 3, let xn is equivalent to xn dashed is equivalent to xn double dashed, then limit of d xn dashed equal to 0, and also limit of d xn dashed xn double dashed equal to 0, right? So using these two limits, you are going to have, so d of xn double dashed is always less or equal to xn dashed plus d of xn dashed xn double dashed, right? And this tends to 0 as n tends to infinity. So that means limit of dxn xn double dash equal to 0. And this implies xn is equivalent to xn double dashed. So it is transitive. So therefore, this implies that the relation defined above forms an equivalence relation. So the relation forms an equivalence relation on the class of Cauchy sequences.
স্যার কিছু শুনতে পাচ্ছি না। হ্যালো স্যার।
হ্যাঁ স্যার, আমি শুনতে পাচ্ছি না।
স্যার কিছু শোনা যাচ্ছে না।
স্যার তো মাইক মিউট করা আছে।
হ্যাঁ হ্যালো, এটা ওই ফোন এসেছিল। ওকে ওকে okay. So the relation forms an equivalence relation, and so therefore using this equivalence relation you can construct distinct equivalence classes, right? So let x cap be the set of all distinct equivalence classes, right? Okay, denoted by, so we are denoting the equivalence classes as like that: x cap, y cap, z cap, etc. Where what is x cap? That is, x cap means where x is a sequence xn, y is a sequence Cauchy sequence yn, z, zn, and like that. Okay, so that means, so x cap means this class constitutes of those Cauchy sequences which are equivalent to x, right? Y cap consisting of those elements, those Cauchy sequences which are equivalent to y, okay, and like this way. Okay, so x cap defines a set of all those distinct equivalence classes. Okay. 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 That means so we write that sequence xn belongs to x cap means sequence xn is a member of x cap. That is, sequence xn is equivalent to, you just take this xn dashed, is equivalent to x equal to xn. Okay. So that is the definition. Okay. Okay. Now, after forming this set, our intention is to make it a metric space. That means we need to define a metric, a suitable metric, with respect to which this set will form a complete metric space. Okay. So what is the suitable metric we can choose? So let us define a map d cap colon x cap cross x cap to R by the rule that d cap of x cap y cap, okay, equals to, so x is a sequence xn and y is a sequence yn, and we are defining this as limit of d xn yn. Okay. Okay. So in this way we define this map, but the question is that does it is it a well defined map? The question is it well defined? Because since these two are classes, and in between and in these classes you may choose any representatives. Okay, suppose from x cap you are choosing xn dashed sequence, and from y cap you are choosing yn dash sequence. Then you can form this limit xn dashed yn dashed. So we need to show that these two are same. Okay. And after showing this, you can say that yes, this map is well defined. Okay. So let us check that whether it is well defined or not. Okay. That means whether the limit n tends to infinity dx and yn exist or not. Okay. Okay. So let us see that yeah. Okay. Firstly, yeah. Firstly, check that whether limit dx and yn exist or not. Okay, so that is a question first, and then we show that for any two other representatives, you will have the same limit. Okay, so firstly we need to check that this limit exists. Okay, that means taking other indices, suppose m, so whether uh, limit okay, so let us we see that d of xn comma yn minus d of xm comma ym will be less or equal to d of xn xm plus d of yn ym. Why it is so? Because using triangle inequality. Okay, and also minus of d xn yn minus d xm ym is again less or equal to d of xn xm d of yn ym. Okay, so combining these two, you can write dxn yn minus dxm ym is less or equal to d of xn xm plus d of yn ym. Okay, now since sequence xn and sequence yn both are Cauchy sequence, right? Are Cauchy sequences. Okay, so the right hand side will tend to 0 because dxn xm tends to 0 as n tends to infinity, and dyn ym tends to 0 as n comma m tends to infinity. And because of this, so mod of dxn yn minus dxm ym is so less or equal to dxn xm plus d yn ym, so tends to 0 as n comma m tends to infinity. And making this limit tends to 0, so you can say that this sequence so this is a Cauchy sequence in R, right? Is a Cauchy sequence in R. And since R is complete with respect to usual metric, and since R is complete, so limit of dxn yn exist, right? So this sequence converges. So limit exists. So the limit exists, okay? But now the question is, whenever you are taking other representatives, then whether they are equal or not. Okay. So in a similar manner, let us suppose that sequence xn is equivalent to xn dashed, sequence yn is equivalent to yn dashed, then using the same inequality here, this one, applying to these sequences, you will have d of xn yn minus d of xn dashed yn dashed will going to be less or equal to d of xn dashed plus d of yn dashed, and this tends to 0 as n tends to infinity. Okay, as because they are equivalent to each other. Using that relation, you can say that this tends to 0, this tends to 0 as n tends to infinity. So therefore, this limit tends to 0, and that means, what does it mean? The limit of dxn yn equals to limit of dxn dashed yn dashed. That means d cap of x cap y cap equals to limit dxn yn as well as d of xn dashed yn dashed. Okay. Okay. So at this stage, you can say that yes, this map is well defined. Okay. Now, okay. Now we need to prove that d cap forms a metric on x cap. Why? Now it is clear that since D is a metric, so D cap x cap y cap is always greater or equal to 0, right? Since the metric D is always greater or equal to 0, so is their limit is greater or equal to 0. So that means D cap x cap y cap is greater or equal to 0. Okay, and if you suppose that d of x cap equal to if you suppose that x cap equal to y cap, then d cap of x cap equal to 0, because why? Because limit of d xn comma xn is 0. Okay, and also if d cap of x cap y cap equal to 0, then limit of d xn yn equals to 0, and then what will happen? That means sequence xn is equivalent to yn, right? So these two sequences are equivalent to each other. Then what does it mean? Just remember the result of equivalence relations, that is A is related to B if and only if their classes are same. That means x is equivalent to y, so their classes will be same, that is x cap equals to y cap. Okay. Number 2, this is very easy. D cap x cap y cap is always equal to d cap y cap x cap. And number 3, for any 3 classes x cap y cap z cap, we will definitely have since d of xn yn is always less or equal to d of xn zn plus d of zn yn. So now taking limit, you will definitely have, so d cap x cap y cap is less or equal to d cap x cap z cap plus d cap z cap y cap. Okay. So now, so this proves that after getting this, so this proves that d cap is a metric on x cap. Okay. So with respect to this map d cap, you are having a metric space x cap d cap. Okay. Now we need to define the isometry. So that is our step 2, construction of an isometry. Okay. The construction of an isometry. Okay. Now let let small a belongs to x, be any point. Okay. And with this point, you can associate a class. Which class? Then the sequence a a a a whose each term is small a, that is a constant sequence a. Okay. So then the constant sequence, and you know that every constant sequence is convergent and every convergent sequence is always Cauchy. So the constant sequence is a Cauchy sequence, right, in x. Okay. And this Cauchy sequence will associate a class, equivalence class. This Cauchy sequence will associate one equivalence class. So this associates an equivalence class denoted by a cap, which belongs to x cap. Okay. So what okay, so what did you have? So you have, for one point, for every point a, you are having an equivalence class a cap in x cap, right? That means you are corresponding each point of x to some point of x cap. So this correspondence gives you a map. So this defines a map T from x to x cap, okay, by T of a goes to a cap. Okay. A cap. Let W be the image space of x under T. Okay, right. Now we see that T is an isometry. Why? Why it is an isometry? Because of the reason that d cap of a cap b cap, right? Okay, so a cap contains the constant Cauchy sequence a, b cap contains the constant Cauchy sequence b b b, right? So that means if you take the limit, it will have dab, only dab. So since the sequence is constant, so it is independent of n. So that means it is dab. That means the distance between a and b equals with the distance between a cap and b cap, and this shows that T is an isometry in between x and x cap. Or you can say that T is an isometry from x onto W. Okay. So therefore T is an isometry from x onto W. That means x is isometric with W. Since P being an isometry, it is always 1 1, and you are having the ontoness. So therefore, you can say that x is isometric with W. Okay. As we have defined that two metric spaces are isometric if there exists an isometry from x onto the codomain space y. Okay. Okay. So x and w are isometric. So now our next goal is to check that. Now we show that W is dense in X. W is dense in X cap, sorry, X cap. So whenever you are talking about denseness of a subspace in a metric space, then you need to consider any element from the whole space. So let us suppose let X cap belongs to capital X cap be any element. Okay. And yeah, fine. And you need to show that every epsilon neighborhood of X cap will contain a point of W, right? Okay. Okay. So let epsilon greater than 0 be given. Okay. Then okay, given. Now let x equal to sequence xn. Okay. X equal to sequence xn, which belongs to X cap, right? Okay. So that means, what does it mean? So since it is a Cauchy sequence, So there exists a natural number n such that d of xn comma xm is less than epsilon by 2 for all n comma m greater equal to n, right? Now put a particular m equal to n, then d of xn comma xn is less than epsilon by 2 for all n greater equal to capital N. Okay, and with respect to this xn you can construct a constant sequence. So let the sequence xn 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 and so on. So this sequence will have to be in xn cap, right? And this implies that this xn cap must be in the space W. So thus, with respect to this x cap, you are getting some point in W. And not only that, now d cap of x cap xn cap. What is that? This is the limit dxn this. Okay, right? So that means, what does it mean? That means, so for this epsilon greater than 0, yeah, we are having n belongs to this such that d cap x cap this is less than epsilon by 2, which is less than epsilon for all yes. Okay, so this implies xn cap is in the open ball centered at x cap with radius epsilon. So therefore, given any epsilon greater than 0, you can search out some xn cap in W, which is lying in the open ball centered at x cap with radius epsilon. So every epsilon neighborhood of x cap will contain a point of W. Okay, and this proves that W is dense in x cap.